Hey, John here. Let's talk about iterators. I'm at cppreference.com. If you come over here and click on Iterators Library, you're going to find out there's a whole bunch of things we can do with iterators. Now, this table down here is the main focus here of this video, all right? I'm going to be talking about these different kind of iterators. Now, if you've used linked lists and vectors, you already know that not all iterators are created equal, okay? And this is a walkthrough of what all the different kinds of iterators are and the different kind of containers that would use them, all right? And what contexts would you use which kind, all right? Now, this is kind of all automatically handled for you. So you don't really have to think about this in regular old day-to-day coding, right? But in specific cases, you need to be aware of this, all right? So the way you read this table, if you start over here and you look at this legacy input iterator, all right? Don't worry about what it is just yet. But you have this box right here, and you have a type of iterator named in here, okay? And over here, these are all the things you can do if you have an iterator that is of type legacy input iterator. Okay, you can read and you can increment that iterator. Notice it does not let you decrement it. Okay, and notice that it says without multiple passes down here. Okay, that means once I have read a value using this kind of an iterator, I cannot read it again. I can read it once, I can increment it to the next one, and that's all I can do. Why? Because it does not say that I can decrement it, right? So I can read it once and only once, and then I can increment it to the next element, and that's all I can do with this one. So this is pretty limited. So what is this thing over here? A legacy forward iterator. What this box in here represents is this one can do everything that this kind of iterator can do, plus more stuff over here, okay? So what does this one add? Well, this one allows you to increment with multiple passes, all right? So this one lets me read the elements that an iterator points to more than once. It'll also let me reset the iterator, like let's say, for example, if this was a list of some kind, I could move it back to the beginning of the list and read the whole list a second time, all right? That's what this thing refers to when it says multiple passes. Now, it doesn't say it in this table. I don't know why. It might be a typo or an oversight on the part of the website maintainers. But these iterators down here, you can also write to them, okay? It doesn't specifically say it. This one says read. I suppose what they had in mind was read only, okay? And it doesn't say down here, therefore we could also write, is my point, okay? So this kind down here, a forward iterator, you can increment it, and you can read the values more than once, all right? So notice these are, this says input iterator, this one's forward, and what does this really let you do? It has to do with incrementing and going forward, okay? Input iterator, you think about that name, well, that's just for reading only, all right? So these names, hopefully, when you see them, it'll spark something in your head of what they really mean. A bidirectional iterator, well, this is the kind of situation we would get if you have a doubly linked list. Right? Notice this is the first type that can allow you to decrement it as well as increment it. I can add one to these iterators to move it forward. That's what increment really means, incrementing it by one. Okay? The bidirectional allows you to both increment and decrement by one. And the bidirectional, as well as the forward, allows you to make multiple passes and read and write multiple times. Random access iterator, okay? Well, everything that all these can do, plus I can have random access. And as we'll see, this is the difference between something like a vector that allows the programmer to directly access any element in the container by using, like, I could say, vector.begin plus 8, and that would be a way to get an iterator that points to the 8th element. I cannot do that, for example, on a linked list. Linked list uses bidirectional iterators, and vectors use random access iterators. This is the reason that those two behave differently when it comes to being able to move an iterator around. This allows you to go forward and backward one at a time, forward one at a time and forward one at a time. Here, this one will let you go forward or backward n at a time. Okay? A legacy contiguous iterator. What does that thing refer to? This is a relatively new concept, even though it says legacy over here. And by the way, all this legacy stuff has to do with the fact that we just came out with a new C++ standard, C++ 20, and these are officially now rebranded as legacy. But the new ones work basically the same as the old as far as the programmers are concerned. The new ones are a superset, but they kind of redefined how they specified them. So they had to give them a formal name. That's all. So these legacy ones are the way the iterators have worked for decades, all right? What is contiguous? Well, like I said, this is relatively new, so you'll see it in the newer versions of the standard libraries. And what it refers to is a container that lays out its elements using contiguous storage, like an array. Okay? So these are kind of a special purpose. It's even a more narrow focus than a vector. Okay? So there's another kind here, an output iterator. This is a write-only iterator. I can't read from it, but I can modify values that the iterator refers to, okay? And just like the legacy input iterator, it's very limited. I can do it once and only once. I cannot make multiple passes. I can only increment it by one. So this output iterator, when I write a value using an output iterator into an element, I can do it once and only once. And after that, the only other thing I can do is add 1 to it. And then I can write over the following element. All right? So this is a one-pass type of situation where I can write elements into a container. Here's a one-pass up here where I can read all the elements from a container. All right? So that's what all these different types are and what they all mean. Now, if you go to the container library, okay, and you go look up your vector and your list, I already opened these up. Here's the list. And you look down here closely in the documentation. Remember, we're looking at the list documentation here. You'll see buried in here some mention that the iterators that are used in a linked list, or the standard list, I should say, is a bidirectional iterator, okay? You look at the vector, and in the fine print, you'll see down here, the iterators that are used for vectors are random access iterators, okay? So this is proof of why the lists, where's my iterator? Here we go. The lists versus vector controversy here. They're both bidirectional, right? But the vector allows you to have random access in addition to the bidirectional motion, okay? So what do we know so far? We know that every type of iterator, no matter what it is, provides the ability to increment it one element at a time at a minimal level of functionality. If it's input or an output, they both allow the programmer to increment it by one. Okay, no matter what kind of iterator you have, you always have the ability to say like plus plus and move it to the next one. All right. Now, if it's an output, you can only write, and if it's an input, you can only read. But no matter what, you can always add one to it. All right, that's your minimum level of functionality. Now, as we'll see, if we look around at the different kind of algorithms that you have available. You see this algorithms library right here? Well, we've already talked about some of these. Well, let's look and see what happens for something like copy and copy if. If you look closely at the documentation here, notice that if we're going to use the copy template function, what's the type of the iterators for the range that it uses to read all the elements to perform the copy? It uses input iterators. What type of iterator does it need to write the data over the destination of the copy? It needs an output iterator, okay? Now that makes sense. An input iterator is the minimum level of functionality needed to just read a bunch of elements so that you can then later on write them into another container. Okay? So if you look closely at these definitions of the algorithms, it tells you the kind of minimum functionality that's needed for this to work. Okay? Now, these iterators are implemented in C++, right? So it turns out that this is a subclass of this is a subclass of that, and so on. So if you have a random access iterator and you want to pass it to the copy as one of its inputs, that's perfectly fine, because a random access iterator is a subclass, transitively, of the input iterator class, okay? And the output iterator simply says that the minimum necessary functionality that it needs is that of the output iterator. Now, it turns out that because all these iterator types right here allow you to both read and write, these two also are going to end up being a subclass of an output iterator, okay? Conceptually, anyway, okay? So these can be used anywhere in the copy algorithm as other inputs or outputs, okay? Obviously, if you have an input iterator, that could only be used as the input of a copy, right? And different algorithms have different requirements, as you'll see that in order to sort a container. If we go back to the page here, if we look up the sort function, this will need random access iterators. See? Why? Because when you're sorting, what you're doing is making multiple passes over the data, and you might be incrementing and decrementing, and you might have to be able to do something like a partition operation when you do a sort. Depending on the algorithm that the sort uses, it might have to say, for example, move an iterator into the center of the container. Okay. So that's how these things manifest themselves in the regular old standard library of things like sort and copy and stuff like that, okay? All right, so where do iterators come from? How do they manifest themselves, right? Well, they come from the begin and the end and so on, right? So if I create a vector and I call begin, I'm going to get an iterator, okay? So what's this jazz with the const iterator versus the regular old iterator, okay? Now keep in mind that a const underscore iterator means that what you have is an iterator that you can move forward and backward, or however the rules apply to the type of iterator that it is, okay? In this case, it's random, so you can go forward and backward, and you can make leaps around the container, all right? Because this is the vector container, right? Now, a const iterator means that I'm not going to ever write anything. Okay, yeah, it's a random access iterator, but because I've created a const random access iterator, I can move the iterator around and I can read elements out of my container, but I'm not allowed to modify them. Okay, that's what this means, right? A regular old iterator means I can read, I can write, and because it's a vector, I can move it around at will to wherever I want it to go. Now, notice that each one of these things is actually a link. I can click on them. So if I click on Legacy Input Iterator, this actually tells you flat out, what are you allowed to do with this thing? I can increment it. I can use the arrow or the star to refer to the value that the iterator is referencing, okay? And I can ask if one iterator of that type is equal to another iterator or not equal, okay? I can also pre-increment it and post-increment it, and I can dereference it and then post-increment it like this, all right? This is all you can do with an input iterator, all right? And this is kind of legalese speak down here, right? But it's what I told you. I can increment it. I can reference the thing that it refers to. And this is kind of important right here, the not equals here. The ability To compare one iterator to another is critical, right? We use this to end our for loops, for example, while printing out the contents of a container. We say, for some iterator equals the begin, and while that is not equal to the end, right? That's the expression we use. We don't say, well, iterator is the begin and while less than the end. And the reason for that is that loop would never work if we had an input iterator. Why? Because there's no less than operator allowed. Okay? That's only allowed in certain kind of iterators, but not this. So if you use the not equals, it'll work on every kind of iterator there is, okay? So if we go back and then look at some of these other ones, legacy forward, in here it'll tell you the more, this will be, again, in more legalese, it'll tell you more about, the fact that it really is the subclass, or at least it satisfies all the functionality of a legacy input iterator and so on, okay? In here, it refers to the thing being mutable. Okay, if it is in fact mutable, in fact, it would be not a const iterator, then it would be mutable, right? This is, again, legalese that simply says, oh, by the way, it also satisfies the output iterator requirements. In other words, you can write to the elements using this thing, okay? And here's where it talks about the multi-pass. You can make more than one pass over the elements. And again, kind of legalese speak. If you rummage through here, it should make some sense. Bidirectional. It's again, it'll say it satisfies the forward iterator, effectively subclassing it, okay? And it also allows you to subtract from the iterator and back it up, in other words, right? As well as post decrement it with a reference at the same time. A lot like you do a pointer. This is the same exact notation that you use to move pointers around when you're pointing to elements of a regular old C array, and that's designed that way on purpose. They're supposed to look and feel a lot like regular old pointers, okay? And that's true for all of these things. The legacy contiguous, this gets into some more details. It's a little beyond this discussion, but what happens is this gives you a guarantee that the elements inside the container are in fact contiguous, right after another, okay? The vector doesn't necessarily guarantee that, but it turns out that all the implementations are that way anyhow, okay? But by adding this to the types of iterators that are supported, certain optimizations can be made by compilers if the internals of the C++ standard library specify this when it's true, all right? That's really why it's there. Now, if we look at the details of the random access iterator, we see even more operations that we can do, all right? Kind of legalese speak again. This one tells you explicitly that I can add some number n to an iterator over here. I know I can move it around in leaps and bounds, beyond being able to move it just one at a time, like I can the regular input iterator, right? I can add n to it, I can put n and a, I can reverse it around, right? So the iterator can either be on the left or the right of the plus operator. That's what this is formally stating here. It can also go backwards by more than one at a time, and the same thing holds true about subtracting it using this notation as well, okay? You can use the square bracket notation to directly reference any element starting with an iterator I, okay? Note this is from an iterator. This doesn't necessarily mean, like, for example, I have a vector and I want the fifth element of the vector. This is more formal than that, and it says that if I have an iterator over here, maybe it points into the middle of the vector, and I have an n in here. That'll be n elements forward from where the iterator is currently pointing, okay? Again, this is another one of those pointer notation things. That'll work the same way. I can also ask greater than and less than, all right? And what this really means is iterator A pointing closer to the beginning of the container than iterator B? Again, the way pointers would work if they were pointing at elements in a regular C array. Same down here. Is iterator A referring to an element in the container that's closer to the end of the container than element B. All right. You can also ask if it's greater than or equal to, less than or equal to, and so on. All right. So these are handy. Okay. But not all containers can do this. Clearly, a linked list cannot do any of these things. Okay. All right. So a linked list is just a bidirectional, not a random iterator. All right. So this is the random iterator. So let's have a look-see at a vector and some simple iterator moves on here. Okay, let's look at the two different ways to do this, right? Now, as I said before, if you iterate across all the elements in your vector to print it out using the more explicit notation like this, and you always say not iterator is the first begin, and while it's not equal to the end, add 1 to it. These operations only require that we have an input iterator. It doesn't require random access. It doesn't require, any other functionality at all. All we're ever going to do is read from it. Okay? So this is, the legacy input iterator. Forward one at a time. Only use the not equals. In other words, we're not using less than because this one's commented out, right? So let's go ahead and compile this up. Okay, run it. And we see the elements of our vector printed out twice because we printed it out using the long form for loop as well as the range-based for loop to print out the same thing twice. Now, because and only because this is a vector, I can also do this, okay? It compiles, it runs, everything's fine. But if I change this vector to a list, now I'm in trouble. Right? The list can do all the same things a vector can, and this is probably not a good name for that variable because it's now a list, okay? But just for the sake of demonstration, this should not compile because a list cannot do this. Okay? Spew of errors, right? That means you put a less than sign in there. Now, as is always the case when you're reading errors from the compiler, read the first one, okay? It's the most useful one. Why? That's your problem, okay? What does it mean to the compiler? Well, it means all of this down here, and you may not really care about all those other problems, okay? So, for all types of containers, or shall I say all types of iterators, this bottom for loop will always work, okay? You always have the ability to use not equals to compare the value of two iterators, no matter what kind they are, okay? Oops. All right? So, trick questions that you'll see on quizzes and exams are right there. Make sure that these things are legal for the type of iterators that are affiliated with the kind of containers you're using. Let's do a quick review of the copy algorithm down here, right? Now, we were just looking at that a few minutes ago. Let's go back and close all these extra windows here. All right, go back to the home page of CPP reference. Now, we're looking in the algorithms library because I'm looking at the copy algorithm, not count. I need to find the copy. Here we go. Copy and copy if are on the same page. Okay, what do we need for the copy? Input iterator for the first and last, and an output iterator for where to put the destination of the copy, right? So that simply means that these two things have to be at minimum input iterators, which is the lowest level of functionality. Any iterator other than an output iterator will suffice for these two arguments. And this one only needs to be good enough to perform the output iterator functions, right? And of course, the vector, since that's what we're using in the example right now, we know that the vector is a random access iterator because it says so right here, okay? Which gives you bidirectional and, any leaps and bounds of movement that you want. And it is a superset of the output iterator, okay? So it's perfectly legal to put one right there, right? So what are we doing? We're going to print out the elements of our vector, then we're going to copy the elements from one to another. then we're going to print it out again, okay? And there it comes as no surprise that we've got these two things going on here. Now, what happens if this is a standard list, okay? It should still work because the requirements for copy are specified at the lowest tolerable level, all right? It doesn't need fancy stuff, right? So when they wrote the copy, they made sure to only require this low-level functionality so that it can be used with as many different kinds of containers as possible. And actually, let's keep this in here because I want to show you an example that may not otherwise be obvious. I'm going to copy from a list, and then my target over here, I'm copying it to a vector. This should work fine. Why? Because these two have to at least be input iterators, and this has to at least be an output iterator. Why won't that work? Okay? It compiles, so that's a good sign. All right, so there's our input vector, and there's our output vector. And a quick recap down here, we printed out vec2 down here after the asterisk. So this works fine. Not only can they be different containers, they can be containers of different kinds. All right, again, pretty handy. All right, and this is one of the features you get by minimally specifying what these arguments are. You'll notice that copy never ever refers to the containers anywhere in its arguments. These are only iterators, okay? Now, I honestly don't know what would happen if I put like the wrong one in here, right? If you said vec from begin and then I said vec to end, all right? If you use two different containers here, that's going to be really screwy, all right? I'm pretty sure the compiler will get this because right now, remember, this vec from is really a list, all right? Not the best variable name, but I didn't want to have to edit all the code to make that change for that type. My point is that the template probably is defined such that these two have to be of the same kind of container to help you not make a foolish mistake like the one that I did here on purpose, okay? So let's compile this and see what it says. It's going to spew all over, and it says, I can't find something that allows you to do a copy from a list and a vector to a, to a vector over here, all right? Now, this is, again, kind of legalese speak, but that's the problem, right? So I did that on purpose. What happens if we do this? All right. Again, these are all great little trick quiz questions and stuff that you might see in a class if you're taking this for credit. Now I have a vector that I'm copying from, and I have another vector that I'm copying to, and I've foolishly made the mistake of saying I want the beginning of the from vector to the end of the to vector. This is, again, still complete nonsense. But because both of the vec from and the vec to are exactly the same data type, the compiler is probably going to allow this. Yes, now what do you think is going to happen when we run it? Well, what's going to happen is when it's reading the input, it's never going to figure out that it reaches the end. Because I mean, think about that, right? The input vector, okay, as I iterate through it, will it ever iterate to the point where the iterator that's reading, this vector up here ever becomes equal to the end of this vector down here? No, right? So anything could happen at all. And it really is up to the way the library is written in here that will determine what's going to happen when I run this. It is possible that they all use some special sentinel value for their end. My point being, if the end of vec2 is represented like by a null pointer or something like that, and the end of vec from also uses a null pointer, then it turns out that even if I do this wrong, and if the library is written that way, and I don't know, I've never run, this is the first time I'll run this live and taking great risk at running untested code in the middle of the lecture, right? What's going to happen here, right? Now, it's possible that it'll do what we want it to, and it's possible that it won't, okay? I am 100% confident that we all know why that broke after me beating this point to death, all right? So the compiler can help you if you screw up some types of problems. It cannot help you if you screw up the kind of problem that I just ran right there, okay? If you valgrind it or run it in GDB or something, I'm sure it'll point out exactly what went wrong when it went wrong. All right, so let's go back to our iterator library again and scroll down and look and see what we got going on down here. There's a lot of details and a whole lot of fancy stuff that's brand new. I'm not going to talk about the new stuff here. And a lot of detail, a lot of C++20, C++20, a lot of fancy stuff in here. Notice this part that says Iterator Adapters. There's a thing called reverse iterator, amongst other things, okay? Let's look at the reverse iterator. You're probably already familiar with this if you've ever used rbegin and rend on a list or a vector or something like that, okay? The reverse iterator starts at the end and it moves backwards to the beginning, all right? Now, this seems kind of weird. Why don't they just have a reverse copy or something? And they do have a backwards copy, right? Because they have that non-destructive reverse order copy library function if you want to use it. So I have this one in addition to that, right? Well, the reason this exists is because, you know, unlike copy, every single algorithm would have to have two variations for forward and backward. If you use a reverse iterator, if your container can supply one, I should say, then any algorithm that expects to iterate from some first to some last iterator positions and use the plus to increment as it goes can be used with these reverse iterators and go backwards, even though it's adding as it goes, all right? And you've seen this because one way to get it, if we look at some code here, here's the same example we just saw. Here's our vector from, and we create a vector to and make sure it's the right size to hold them all. If we just simply go from rbegin to rend, and then we put the target into vec2 at the beginning, we're using a regular old copy, we'll see that this is going to end up traversing and copying them in reverse order. All right, comes as no surprise that this is backwards from there, okay? Now we can also do this the other way around. We can run through the input vector in forward order and then store the results backwards into the target vector. Should end up with the same thing. Okay, again, it's backwards. If we really wanted to, we could do the whole thing backwards. This is sort of like the backwards copy, right? Go backwards from beginning to ending of the input and go backwards in the output, right? Now it'll come out right because both of them are reversed, right? And backwards of backwards is, of course, forwards. Another good place for trick quiz questions. All right, now let's look at these so-called insert iterators, okay? See this back inserter, there's a front inserter, an insert inserter. A little redundant sounding, right? Let's look at this back inserter. What does that thing do? Well, we can create one of these back insert inserters, okay, by calling the standard :back insert inserter, and we give it a container in parentheses like this, okay? So what is that thing going to do? This will take care of our other problem that we had when we had to have an array that was pre-allocated to, you know, the size or bigger number of elements in it so that the copy could just write over them, okay? If we use a back inserter, instead of just saying vec2 dot, you know, begin over here, which we saw in the last examples, instead we do this, what's going to happen is the copy is going to be inserting them to the end or the back of this vector. Now, for now, let's leave this size the way it is and see what happens. All right, so what happens here? Well, remember when we created our, 2 vector, we initialized it to have enough room to hold each of the 8 values that would have been copied into it in our previous examples, right? But because we used a back inserter, it put it at the end, or it appended them to the back of the array. So if we just wanted to make a copy of one container into another fresh empty container, we don't have to create one that has, we don't have to just use copy and overwrite them. We can create an empty one like this, okay? And then we can just insert them into the back of that vector. And now what will happen is we will have made a copy without having the pre-allocated elements in there that then get overwritten. This is probably more efficient if you think about it, okay? Because if when we ran it up here, or in the previous examples where we created all these empty strings and then took the apple string and copied it into the first one, and a berries and copied it into the second element, and so on, what happened was the program had to create an empty string when it created the vector, and then copy a new string over the empty one. Right? It's doing like twice as much work there. Right? If we use a back inserter and create an empty vector, then what happens is it can create the string and insert it all in one fell swoop. And in the end, the program will run more efficiently. If you did it, a million zillion times, your program would be faster this way than it would if you just used copy without a back inserter and pre-allocated a bunch of elements only to overwrite them right away. I know it should be somewhat obvious that if you use a back inserter, you have to use it on a container that allows you to use a pushback operator, right? If we use a front inserter, for example, this is not going to be supported by a vector, because a vector does not have a push front method. Okay? This will only work on something like a list or a deck. Okay? But otherwise, it will do what you can intuit from the back inserter, right? It'll just put them in the front instead of the back. What about this insert iterator? Okay? I said that wrong last time I said it, I think. Just ring a bell. What's an insert inserter? Anyway, insert iterator. Okay, what does this do? Okay, well, this allows me to do, sort of like the back and the front, but this will allow me to insert the elements wherever I want to put them in the target container. Now, this you have to be more careful about, right? The efficiency of this can go down if you did it on something like a vector, right? A vector will let you insert something, but you probably want to use something like a linked list. Now let's look at the example that they provide in the website here. This is pretty straightforward. They mixed it up and they added something else in here just to make it weird. But let's walk through this and see how this thing works, all right? They got a vector of integers, they have a list of integers, and they're going to insert, what are they going to do? They're going to copy begin to end from the vector, all the elements there. It's the source of a regular copy. And then as the destination, they're going to create an insert iterator of type list of int. And they're going to give it these arguments when they create that insert iterator. L is the list, okay? And this iterator here is the target location. Now, they made this screwy by putting a next in front of begin. If they just put begin, what it would do is it would insert 1, 2, 3, 4, 5 at the beginning of the list before the -1, -2, -3. But look at the sample output down here. It says -1, and this says 1, 2, 3, 4, 5, and then it says -2, -3. All right. So what is this thing doing? If you click this, you can see what it really does is it just adds 1 to the iterator. Okay. Next, it returns the nth successor iterator of IT with a default of 1. Okay. So really, they're just saying insert them starting at the second element from the beginning. Begin plus the 1 default next value. All right. Now this is kind of a neat website. You can hit click and click run. It'll run it and give you the output down here. So let's go ahead and delete this standard next. Oh, what do I got? How do I edit it? Can I not? Oops. I don't think we could edit these things. All I can do is run it. Oh, there we go. Now I can edit it and I can run it. Okay. If we remove the standard next, this is my point. And we can say, okay, I want to insert them at the beginning of the list, right? So this is the output of the last time it was run. Okay, we can then click run right here. So it's going to compile it and run it right there. So now you can see 1, 2, 3, 4, 5 followed by the negative 1, 2, 3. All right. So there's the original example again, right? Started at the second element. And we see it in there. What if I want to start it at the third, right? Well, you're thinking, oh, well, I got a list. I can't just, move that iterator randomly around, okay? Well, it turns out that standard next is smart enough to use standard advance internally, and that's what advance really is for. If I really want to go not to the next one, but I want to go to the next 2, the standard next call will it'll execute a loop, and it'll move it forward 1 at a time in order to get it over to 2, okay? So now when I run it, you'll see, watch down here, the output, it'll all move over 1. Negative 1, negative 2, and now there, okay? And if I say move it over to 3, okay, not a problem. Now keep in mind, this is inserting, right? So I just said put it in, after the third one now. Remember, this is the next one. So the first one is here. The next 1 is here, next 2 is there, next 3 is the end of the list. Okay, so what would happen if we put a value in here that's too big, right? What if I go here plus 4? Well, here's plus 1, plus 2, plus 3 is at the end. Well, where does that go? This is probably undefined and broken. So what happens here? It's got a 1, 2, 3, 4, 5, and then negative. It ended up back at the beginning. Well, that's weird, right? So yeah, don't do weird things that are nonsensical and illegal. I mean, God knows what'll happen. Look at that. It's kind of going around and around. It's acting as if it's a circular list almost. I wonder if that's actually a feature of the next function. That'd be a handy thing to know. Let's read more closely in the doc here. Returns the nth successor. It must meet legacy input. No, it's the expression often compiles, but not guaranteed to do so. Yeah, a bunch of legalese and some goofy stuff. Does not compile while begin. Blah blah blah. It's probably undefined. I would not count on it wrapping around like we just saw it in that example. Now, let's look at these stream iterators. What's up with this, right? An I stream, an O stream, and so on. What's with these guys? Well, it turns out that if you use an I stream iterator, you can make something like standard in look like a container with an iterator on it. Okay, now remember back at the beginning here when we looked at the iterator library top level page, there's this weird thing about legacy input iterators and legacy output iterators. The fact that you can read it once and only once, and you can't go back and read it again after you've read it, and the same thing happens with the output iterator. You can write it once and only once, and you can increment it, but you can never go and write it again. And you can't move it back and forth. Well, guess what these are, okay? Standard in and standard out are a lot like this, okay? So these lowest level types of iterators map very nicely onto C in and C out. So somebody created a iterator adapter so that we can make C in look like an iterator. So let's look at some code that uses one of these. So how do you create one of these things? Well, first of all, you got to make sure you include the iterator header file. And then what do we got here? We have an empty vector. Okay, vector of integers. Nothing's in it. Then we create this iStream iterator that can handle int. The int here has to match the container type, right? And it's going to use as its input stream cin, right? Remember, the copy needs an iterator here. It's a forward, an input forward iterator. And then it needs another iterator here that represents the end. Okay? So they provide this notation here so that you can create an iterator for the input stream that represents an EOF or like an error condition, so that it knows when to stop reading. Otherwise, how would you stop it, right? So this is a weird way, right? This is the notation they use. They say create one of these iterators that represents the end of this of the input stream, or like an error. Like, it's reading integers. So if I type in ABC or something like that from the keyboard, and it will cause this to stop copying, right? So the output, I'm going to use a back inserter, and I'm going to put it into this vector here. Then I'm going to just print out the vector like we've been doing this whole time. All right, so let's go ahead and compile it up. It's already done. So here we go. What are we going to do? 87, 23, 92, 55. And then I'm going to hit Control D for the end of file, and you can clearly see I just read in this from cin, and I filled it into a vector, and then I printed that vector out. Okay? And as I mentioned before, if you put in a bunch of numbers in here, you're going along, and then you type A, B, C, D, E, F, and then you some more numbers and stuff like that, it's going to stop here because it can't, convert that to an integer. All right? So it basically does the right thing when it runs into an error. Okay, so this is not only EOF, but it's also, an invalid conversion would cause this to trigger and represent the end of that stream. Okay, so this is a fancy way to read stuff from standard in right into a vector. Okay, provided that you've got the appropriate data types in here. If they're all the same, no problem. Just use the copy algorithm, all right, with the appropriate iterator adapters. No, it shouldn't come as a giant leap to see what happens with an O stream iterator. It would be the same thing to write something to standard out, okay? Now, we could easily modify this program a little bit and create a completely worthless example of something that reads from standard in and then writes to standard out, just copies it, right? I could easily say this and change this to O stream iterator. This is almost a pointless example here, but I could say standard C out like this. And all I'm doing now is copying all these elements one at a time from standard in to standard out, okay? There's really no need for this vector anymore. Well, I'll just comment it out. I don't want to wreck my awesome example program here, right? I'll just comment all this stuff out. So all he's going to do now is read and convert integers from standard in until he gets EOF or an error, and then write them to standard out. So we should see a written cat, right? But for integers only, of course, right? So 1, 2, whatever, a bunch of numbers here, and maybe we'll put an error in here, and we can see it wrote out what? 1, 3. Of course, it would be nice if they had spaces in between them, right? And it turns out there's a way to do that too. I believe what you can do is you can put a second argument in there and say, this is what I want to use for my delimiter. Where is it? Iterator, blah, 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 blah. It's these voids down here. So in their example, they probably did one down here. Yeah, see the second argument right here? You can put a delimiter in there. Let's set our delimiter to, XXX so that we can see it. When you use spaces when you're trying to learn something and it's writing spaces on your screen, you can't see them. So you don't really know where they are when they show up at the ends of lines and stuff like that, which is, in my opinion, very annoying. All right, so now we can see what we're doing, like 1, 3, whatever, 5 or something like that. So it prints out the 1, the triple X, the 3 triple X, 5 triple X. Now it's waiting for more numbers, right? You can put multiple spaces in here, and it'll be fine. You can skip multiple blank lines. Oops, I hit a W. So that was an error right there. That's why it stopped after the 2, okay? Let's run it again. You can put a tab in there. You can put multiple tabs in there, as long as it can still do the conversion, right? and you can see what this thing is doing. Eventually, you can hit Control D to have the end of file. And I personally find it a little bit annoying that it always prints the triple X's, even if there's no more data coming. But if you think about it, it's kind of hard for it to know whether there's going to be another element or not. So this is, whatever. It's nice. I mean, you can put comma-separated values in here. That's kind of what it's really sort of for. It's kind of handy. Let's go ahead with a comma and a space. Run that one, read in a bunch of numbers and then write out this comma-separated thing. But if you then hit end of file there, this is not always what you want, okay? So if you're going to use this, just beware of the fact that it's always going to put an extra one after the, every one, including the last one, right? Sometimes that's not tolerable, in which case, you may have to do this some other way. All right, before we wrap this up, let's look at one last example here. All right, same kind of thing, right? We're using the OStream iterator to write into standard out, and we're putting a comma after each element. But this time we're going to just copy the elements from some vector of strings up here, all right? So we've seen that before, and this is a regular old copy as far as the input's concerned, and we're using our adapter, okay? And we're going to print it to the screen. So let's compile that up. Run that, and we see, okay, neat way to just dump out a vector. But of course, we've got this extra comma and there's a missing carriage return. That's a little bit annoying, especially if you're trying to write it to the screen. But carriage return is easy enough to fix, right? Just put a end line in here. Oops. And now we've got that taken care of, right? So at least it puts this on a new line. How do you get rid of this annoying comma? All right, well, here's one simple little trick. It's a little annoying and it's not beautiful, but remember, I can do this on the end iterator of a vector. Okay, I can subtract 1 from it. So what it's going to do is print all but the last element in this copy up here. Okay, now down here I can also say end -1 to end and not put a delimiter after it. Okay, all right, it's not beautiful, but it's one way to do it. Okay, and if you're writing a template function that was supposed to create a CSV thing, you might actually end up in a situation where in a template you might have to do something like this because you don't really know what's going on in the container and the higher level code. This should take care of that extra nasty comma, as you can see down here, and it does what you would expect from a comma separated value type output. So what's the takeaway of all these adapters and iterators and stuff like that, right? Well, the standard algorithms can be used to do more than you might think. With iterator adapters, we're, reading a vector, printing it to the screen with commas between it and stuff like that in this last particular example. All right, so you can mix and match these algorithm functions like copy with regular old iterators or anything you want as long as there's an adapter for it. All right? So, thanks for watching. See you next time.